Hello and welcome to this video on states of matter. Now, not only are we looking at states of matter, also looking at changes of state and also at what's the evidence that the particles actually exist. So quite a bit to get through, so let's crack on. Okay, the first thing we're going to do is compare gases, liquids and solids. Basically answer the question, so what's the difference between them? Well, we're going to look at 5 properties and they are as follows. Volumes. First of all, volume is how much space something takes up. So I've got a coffee mug in front of me. It takes up a certain amount of space. Second property, what shape? Well, the chair I'm sitting on is sort of chair shaped. It's fixed. Density, weight compared to size. Compression. Now, although I'm nearly 80 kilograms, even I can't compress this seat much at all. So compression is how much something can be squashed. And lastly, ease of flow. Okay, let's look at each one. Start off with solids first of all. Now, solids have a definite or fixed volume. So the mug I've got, it's got a fixed volume. Then a definite shape. Yeah, I'm looking around at all the solids where I'm working from. They've got a definite shape. High density. Solids are pretty heavy compared to their size. Cannot be squashed. So as I said, the chair I'm sitting on cannot be squashed. And solids do not flow. I can't pour a solid. Well, what about liquids? Well, liquids have a fixed volume. So the coffee I poured into my cup a minute ago, it's got a fixed volume. Shape, well, the liquid has a shape that matches that of the container. So when I poured the coffee into my coffee mug, it has the shape of the coffee mug. They are medium density. They're less than solids. Cannot be easily squashed. Thankfully for hydraulics, i.e. the braking system in a car, liquids cannot easily be squashed. But liquids do flow easily, so when I poured the coffee into the cup, it went very easily. It flowed nicely, as you'd expect. Right, what about gases? Well, gases fill the container they're in. I'm sat here recording this in a room at home, and the gas is filling the space of the room. And the shape becomes the same as that container, or the same in this case as the room. They've got very low density. Gases can easily be squashed, so you do not want to have gases in your braking system in a car, because if they can be squashed, the brakes will fail. And gases, you can't actually see them, but they flow pretty easily. So that's a good comparative table there of the differences between gases, liquids and solids. Let's look at each state in turn. Let's start with solids. Now, solids, between the particles here, there are strong forces of attraction. They're held in a fixed position, you can see here. They've got lattice arrangements, so we've got these rows and these columns fixed as a lattice. Don't move. The particles do not have enough space to move, so they have a definite shape and volume. All they can do is vibrate from side to side. Now, if you heat solids, as they become hotter, particles start to vibrate and they're pushing on the particles next to them, and so the solid can expand. But look, there's no spaces between them really, so it can't be compressed, and because of that they're generally very dense. Let's go back to heating. So when heating, molecules gain thermal energy. They vibrate more and more, and they start vibrating and pushing particles next to them, which means that strong forces between particles are overcome. The molecules start to move, and at that point we say they are melted and they become liquids. So liquids have some attraction between molecules, not as much as solids, but some. They're free to move, so you can pour them. No definite shape, but take the shape of any container they put in. And in that container the molecules are in constantly random motion. Okay, we can't predict in which way the particle is going to move. It's random. When heated, as with solids, the particles move faster and expand, okay, pushing against each other. They can't be compressed and they're quite dense. Going back to the heating, the heat makes the molecules move faster as they gain energy. Okay, they gain energy, so the thermal energy converts into kinetic energy as they move faster and faster. Fast-moving molecules at the surface, this is your cup, so those particles on the surface will overcome any forces of attraction and they'll escape. And we call that evaporation because they've changed into a gas. Right, now between gas particles, as we have over here, there are no forces of attraction. They're free to move and they travel in straight lines. Sometimes they collide, particles do collide. They have no definite shape or volume and need to expand to fill the space available. They exert, if they are in a container, they will exert pressure on the wall of the container. The collisions of the particles against the wall of the container creates pressure. They're constantly moving randomly, as we said, move fast when heated, can be compressed, very low density, like in a balloon, so a balloon can float. Yay! Now, when heated enough, molecules have enough speed and energy to overcome forces and escape each other if they are in confined space. Molecules break away in a big bubble of gas, boiling. So you look at your kettle, when those bubbles come to the surface, it's molecules of gas bursting out and escaping. How exciting. Now, substances can change state, usually when they are heated or cooled. They can go between solid, liquid and gas. For example, liquid water turns into steam when it's heated enough, and it turns into ice when it's cooled enough. State changes are reversible. Ice can be melted, then frozen again. These are physical changes. There's no chemical change going on. They're physical changes. So let's build up a diagram now to show the various physical changes. Here we've got the three states: solid, liquid and gas. Now we have names for these changes. So going from solid to a liquid, we call it melting. Going from liquid to a gas, we call it evaporation. Going from gas to a liquid, that's called condensation. Liquid to solid, that's called freezing. Now there is certain examples, only very few, where certain substances bypass the liquid and change straight from solid to a gas. So sublimation is a change in state from a solid to a gas, or gas to a solid, but they don't bother becoming liquid in between. An example of sublimation is dry ice. Solid carbon dioxide changes directly to gas. So solid carbon dioxide doesn't bother becoming liquid. It goes straight from solid to a gas. Now, as physical changes take place, there's an increase in internal energy going from solid to gas and a decrease going from gas to solid. Now, this is because when a substance is heated, energy is put in. Heat energy is put into the particles. Its internal energy increases. Au contraire, on the opposite, when a substance is cooled, its internal energy decreases. So, as a solid is heated, so particles gain more energy. They gain energy going from solid to liquid. We see the changes now. And then the particles move more, weakening forces causing expansion, and so they melt. At a certain temperature, particles have enough energy to break free, and it's called melting. So as they are heated, they're gaining thermal energy. As heating continues, particles gain more thermal energy, so move faster, weakening forces further. And at a certain temperature, particles have enough energy to break free. We call that boiling. So as we're going from solid down here to a gas up there, the particles are gaining internal energy supplied through thermal energy by the heating, and they'll use that kinetic energy to move about and so on. Now, the particles in a substance stay the same when it changes state. There's no change to the particles whatsoever. Only their closeness and arrangement or motion change. This means that the chemical nature of the substance itself stays the same. So going from a solid to a liquid, going from ice to liquid water, it's a physical change. There's no chemical change happening there whatsoever. It's still water. This means the chemical nature of the substance itself stays the same, and the mass of the substance stays the same. When I melt, say 100 grams of ice, I end up with 100 grams of water. There's been no chemical reaction taking place, and this is called the conservation of mass. Similarly, if I have 100 grams of water and I freeze it, it becomes 100 grams of ice. Physical change, no chemical change. Now here we've got a little graph showing what's happening. So along the x-axis, which is here, we've got time. On the y-axis up here, we've got temperature. Now as we put energy into a solid, we reach a point where there's no further change in temperature here, but it'll change from being a solid to a liquid. This is called the melting point. Similarly, a liquid is heated. At this point, called the boiling point, it changes to a gas. And we can look at the opposite of that as well. As a gas is cooled, it reaches a certain point, a specific point. Now, it's worth mentioning here that for chemical substances, these temperatures are fixed. So water has got a fixed point here of 100 degrees Celsius. So this is exactly here, 100 degrees Celsius, and it's moving between a gas and a liquid. So 100 degrees Celsius is the fixed condensing point, or boiling point if you like, for water. Liquid then cools and cools and cools, and another fixed point is found here. This fixed point here is called the freezing point, or it could be, on the previous diagram, this, if you remember, was the melting point. Now at this point, okay, the liquid, if it's water, is changing into solid ice. So these are fixed points. For water, it's 0 degrees here, 100 degrees there. Okay, if it's any different to that, if you've got water and you heat it and it boils 102, you know it's not pure. Only pure water boils 100 degrees Celsius. Only pure water freezes at 0 degrees Celsius. Okay, remember that. Okay, now let's go on to the last part now, looking at particles. Now particles are very, very small. But what evidence is there they actually exist? We talk about particles, oh yeah, particles, blah, blah, blah. But how do you know they actually exist? Well, the two simple experiments help us to prove their existence. First of all, dilution of coloured solutions, and secondly, diffusion experiments. Let's start looking at dilution of coloured solutions. Now, suppose you got here a beaker of water, and into that beaker of water we drop a blue copper sulfate crystal. What's going to happen? Will the blue crystal stay there? No, it won't. It will spread out. We talked about this spreading out to fill the available area. We end up with a blue copper sulfate solution. We don't get like darker blue down here and lighter blue there. It's a uniform blue colour because the particles are spread evenly. Now suppose we take 10 cc's of that copper sulfate solution, put it in there, and add 90 cc's of water. What we find is the solution becomes paler. Why is it paler? Because there's less copper sulfate particles present, but they are still there, and we can see they are still evenly distributed in the container. Let's repeat. So let's add 10 cc's of copper sulfate solution to another 90 cc's of water, and again it gets paler. The copper sulfate particles are still there, they are still evenly spread out, but there's just fewer of them. Let's do it again. So here we take 10 cc's of copper sulfate solution, put in there, add 90 cc's of water, and you can see we have still got copper sulfate particles here. Okay, it's getting paler, which means there are fewer copper sulfate crystals, but they are still there. And we could go on doing this over and over and over and over and over and over again. I don't know how far, but we could do, and we'll still have the particles. Okay. Now, serial dilution. This is called a serial dilution, where you're diluting it bit by bit by bit of a solution, such as copper sulfate, provides evidence that the original crystal was made up of many small particles that spread out evenly when the solution is diluted by adding water. So particles exist here. There's less particles there, but they still exist. Less particles here, they still exist, and so on and so on. So that is serial dilution, to prove the existence of particles. Another one is the classic diffusion experiment. Now, I don't know what it was about my bedroom at home when I was a kid, but my stepmother would always come in and spray air freshener in the corner of the room. I don't know if I was smelly or what. Okay, so she sprayed it in the corner of the room. It was a horrible rose smell. I used to hate it. What then happened was the particles were spread out in all directions. And no matter where I went in my room, I could still smell it, because eventually the particles occupy the whole room. Okay, so particles move from here to occupy the entire space. So everywhere in my bedroom, it still smelled those damn roses. Now, that was an example of diffusion. Other examples of diffusion include, you know what it's like, you're lying in bed and someone downstairs in the kitchen is frying bacon. That lovely smell wafts up the stairs. That's diffusion. Leaking of air from inside a balloon. Well, you know what it's like, have a birthday party and outside your house you tie some balloons, okay, put on the garden gate perhaps, and there they are, full of air, really nice. Leave them a few days, what happens? They start to deflate and deflate. Reason being that air is leaking or diffusing from inside the balloon. And lastly, sugar. Now sugar, I don't have sugar in tea, thankfully. Oh, horrible thought. But some people put sugar in their cup of tea. Now if you left it and didn't stir it, the bottom bit would be sweet, top it wouldn't. But if you stir it, the sugar particles diffuse throughout the liquid, and so the whole cup of tea tastes evenly sweet. Or so you hope. Now, just define it. Diffusion is the movement of particles from areas of high concentration, with lots of them, think about that air freshener in my bedroom, to areas of low concentration until they're evenly spread. Diffusion depends upon random movement of particles. So we're proving here, actually, particles do exist. So particles exist and they move about randomly. Diffusion is slow in liquids than in gases, because liquid particles are not as free to move as gas particles. And diffusion in solids, does it ever happen? Well, it happens to things like jellies. Jellies aren't really solids, they're more like colloids. But solids, no. But we can see there diffusion in gases and liquids does happen because particles exist and they move around. Okay, right, well in this video we looked at states of matter, we've looked at changes of state, and we looked at evidence of particles. I hope it all makes sense to you. Really I'm grateful if you're watching this video, and I'll be back with another video very, very soon. So bye bye for now.